Okay, welcome back. I wanna basically revise what we did the last time. The spring break is good and all that, but sometimes it's bad because it flushes everything out of the head or something. Okay, so we will discuss. We started chapter 9, which is on jointly distributed continuous random variables. The number of adjectives is just increasing. Jointly distributed continuous random variables. So just to make it clear, the exam on Thursday will have jointly distributed discrete random variables. That is chapter 8. But this is chapter 9. It's not on the exam on Thursday. Okay? So this one is when the two variables that are joined are continuous. So when that happens, a lot of wrinkles happen. So I will just so first of all, you need to imagine what am I even talking about? What is a joint density? A joint density is a surface. All right, a joint density is a surface. This is a simple one. This is a quarter unit high, and it floats above the box made by -1 to 1 for both x and y. Because we explained what this is last time. The good thing is you don't actually need to bother drawing this because this is not the issue here. Of far greater importance is the region where you are supposed to integrate. Okay. So, for example, how do you answer a question like this? All right. How do you answer the question? What is the probability that you lie inside that sub box or whatever you call it? Okay. So look at what I did last time. What you do is you draw a picture. If you draw a picture like this, see, I have shown the entire region where the density is positive. So that's the one. But the region of interest is this smaller box now. I have colored this red. So what you need to do is to find a probability, you know that to find probabilities from densities, you integrate. So now this is no different. It's just that this integral, unfortunately, if you have not done this kind of integration, this is new. That's why I'm spending a little bit more time talking about this carefully. So you want to perform this integration, which means you must now integrate over, well, non-intervals, which you may not have done before. That's why I'm doing it pictorially. You want to integrate over a box, a red box, essentially. So look at what I've done. There's nothing to freak out here. And most of you actually did not freak out because I gave you a group work and you did really well. You set up the limits correctly, so we'll revise that again. How do you set up the limits of integration? Let's say, go back to kindergarten when you first were given crayons. So just ask yourself, how do you color a box? I know I color it diagonally now. Okay, that's a very bad example. Okay, don't follow this. Right? You color it in a certain orientation. So if I choose to color X first, I go in the X direction. You take your lines and you draw them this way. So you just ask yourself, okay, to color this region, all my X's will always start at -half and always end at half. Do you agree? And it's not enough to just draw the one line like that, -half to half. You have to draw a variety of lines that start from here and go all the way to here. And that means these lines will start, all these horizontal lines will start at 0 for y and travel all the way to 3 for x. If you did that, you would integrate over the box in this orientation. I think it's not too early for me to tell you. There are other ways to color this. You can color it radially as well. It's a stupid choice because this is a rectangular box. But if there will be future problems, which I will, if we have time, I'll show you. There are multiple ways to do this. Have you heard of polar coordinates? And Jacobian and things like that. So there are things you can do that do not have to be in a Cartesian framework, but the idea is exactly the same. How do you color the region? You can color it radially, which, as I said, that's like fitting a round peg into a square hole or whatever you're going to say. That literally doesn't work in this case. It's a very bad choice, but you could do that as well. So the other thing that's sensible would be to color it in the opposite direction. And by the way, okay, let's talk about the mechanics of how do you integrate things like that. You just take out the constants come out of integrals, you know that. You're left with a 1 here. How do you integrate 1 respect to x? It becomes x. And that reduces the problem to something that you're very familiar with, because this becomes a one-dimensional integral, which everyone knows how to do. Now, I do expect you to know how to do pretty basic integration on the exam, just so you know. Like integration by parts is, I'll give you a heads up. Integration by parts is going to be on the test on Thursday. So just make sure you brush up on that. It's not going to be some monstrosity. It's not. But you do need to know how to do integration by parts. So just make sure you check up on that. Okay? I'm giving you some notice. All right? Okay. This is not integration by parts, right? We might see some today. I hope we will. I think we might actually. So we'll see. Okay. Alternatively, you can color boxes in the other orientation. You can color them vertically first, and then draw the lines moving in the x direction. So you see the dy dx now. So do you agree with this? Now, I believe I assigned this, I think. This was one of the ICPs I think I asked you to do. Most of you got it right, some of you did not. So I'm giving you the answer now. So look carefully. I'll explain. Why is it like that? Because, first of all, why do you need to think about it this way? If I color this in the y direction first, then all my lines would start at here and exit at 3/4 like that. And then all my x's would go from -half to half. So it's just how do you choose to orientate your coloring of the region. Okay, so that I may be wrong. Maybe this was not the thing I asked you to do. I can't remember. Okay, I think it's this one. Sorry. Okay. Now here's a more complicated problem. Same density. What is the probability that x and y hang around here? That's what this is trying to say. You know you need to integrate. The region that you want to integrate is just a little bit more fussy now. Draw it. Well, here it is. This is the region 2x minus y is positive. It's here. Notice, I don't care about that 1/4 surface flying on top. That's actually immaterial. That's nice to look at. It will make a cool YouTube video to show things moving around. But actually what counts is the projection. You look from above, where does the shadow fall of the thing that you want? So you want this region, you want to integrate it. How do you integrate here? See, I always start by saying integrate the region of interest, and you set it up. So we did it this way in class. The wise choice, the smart choice actually here is to do dx dy. Why? You don't need to change definitions, because if you color this region this way, no rules change. It's just that the lines get longer, yes, but that's governed by these relationships. So if I color in the xy direction, x first, ask to draw a generic horizontal line like that. Where does it come in? It starts on here. What does it mean to start here? Do we know the equation of this line? Of course we do. Right? So this is the line y equals to 2x. So what am I saying? It means I always come in at x equals y over 2. That's the relationship that governs x and y. If you say you start from this line, that's what a line equation tells you. It controls how x and y behave together. So you start at x equals y over 2, and you go all the way to a fixed line 1. This is a vertical. You always stop at 1. You come in at different places, yes, but you always leave here. Then, how many vertical lines must you draw? Well, uncountably many, but you get the point. The range is everything from y equals -1 to 1. That will fulfill the end. Now, the rest is just mechanically doing the calculus, which is a little bit tedious, I admit, right? Okay. Then what I did give you for the ICP, which I was pretty pleased, is I think almost every group got it correct or partially correct. So let me show you the answer. If you are the group that did not get it correct, then pay close attention. If you chose to do dy dx, which would not be as wise a choice, but I wanted you to practice, if you color it in the dy direction first, you need to change rules, because this picture, by the way it is set up, it changes its definition halfway. If you are coloring this part of the picture, all your lines will start here, dy first, and end here. And we are all fine and good until we reach here. Once you reach this point, to color this, it actually becomes easier. All the lines now behave the same. So break up your work. We know that as long as your x is less than 1/2, this is the rule that governs it. The lines you draw will always start at y equals -1 and extend up to the straight line y equals 2x. But this is only true for lines that are between -1/2 to 1/2, according to the picture. After 1/2, the rules change. After 1/2 all the way to 1, every line you draw starts at -1 and ends at 1. So this is actually the easier region to set up. Now, this has to be solidly understood, because if not, this chapter will be totally mind-boggling, because basically probability is integration. And when you have two random variables that are continuous, the integration just gets a little bit more involved because you're now looking at two-dimensional. Okay, on a plane. Is this okay? All right. This is the answer. And I would have indicated on your sheet if you got something a little bit wrong. I put a circle there. This is the answer. Now, the rest is just, as I said, mechanical. So I don't want to dwell on that, but you get the answer. What about another question? I think there was one more. Yeah, this is kind of a trick because x plus y absolute value less than 2, if you drew a picture of this region, it will cover everything. X plus y absolute less than 2 looks like this. Do I actually have it? Oh, I don't have it. I have it here. Sorry. Yeah, so if you took the time to draw this region, and I encourage you, if you are not so confident with these things, just make sure you know how to get this region. You draw the straight line. Okay, what does this mean? This means x plus y is between -2 to 2 without the absolute value sign, right? So draw x plus y equals 2. Draw x plus y is equal to -2. You get two straight lines. And then just ask yourself, this is the region that traps everything inside there. And you will find that this region traps the entire box originally, the one with the dotted line. So the probability is 1. You're always there. X and y will always fulfill this, and the probability of this happening. All right. Then we went on to another example. This one. See, I gave another PDF. We used Wolfram Alpha, or I used Wolfram Alpha to draw this. It's a plane. It's a plane. I think I'll just show it to you since we are here. Yeah, I have the plot here. Okay, it looks like this. But again, that's not important, but I just want to show you that's what the plane looks like. The plane z equal whatever looks like this. In other words, now I do like students to have some intuition. The higher it gets, the more time it spends around here. The probability is proportional to density. That's what density is. That's why it's called a density. It's more dense here. So people will hang around here more. The probability will be higher. All right. So, but how do you do the integration that you need to do? Find k. So you know that every density has to integrate to 1 for it to be a valid density. That is true from the start. All densities are only densities if they integrate to 1 or sum to 1. And so do that. So you know that this integral must go to 1. Why are the limits so easy? Because this is an easy setup. The place where the density lives is all x and y are trapped in a nice square, not even a rectangle, 0 to 5. It's very easy to color a square. I don't know whether you noticed. 0 to 5, 0 to 5. That's it. So there's nothing to think about. So in this case, very easy, straight up integral. I'll just, since this is new to you, integrate respect to x, constant, tack on an x, variable 2. This is treated like a constant because you're integrating respect to x. Treat this, leave this alone, put an x there. Then it becomes very important for you to indicate, yeah, what variable is 0 to 5, so add an x here. Or not, trust me, you get very confused. Don't just write 0 to 5, yeah, who's 0? Right, x. Then just do this, the usual calculus. All right, so you can find your k, which was another ICP, which you did get correct, 1/375. So good exam technique, as I've said a few times, is even if you have found K, in your future, we'll just leave it as K. It makes it easier for me to grade in case your K is wrong. Right? You don't need to know K, actually. You can leave it as K. Okay, now find this probability. How do you do that? See, this probability again is showing you don't integrate over the entire region. You don't want the entire region now. You want this subset of the region and so on. It should look like. Is this okay? Again, I don't want to waste time on the calculus. It's very irritating. That's the answer. Okay, like that. Okay, so today we will start to venture into something which I think we did not do the last time. So this is example 147. Assume the joint PDF of x and y is this thing, okay? Don't freak out about the density because do we actually even care what this looks like? By the way, if you want to know, this is going to be like a I don't know what looks like that, so I can't even describe it. It's something going down. It's exponential, but it's a 3D exponential kind of thing. Okay? Spends most of its time close to zero and dies out very quickly. The important thing is, where's the region where the density is positive? X more than zero, Y more than zero. So do you notice something? This is your first time doing something where the region of positive density is an infinite. In fact, this is actually called the first quadrant. X greater than 0, Y greater than 0 is the first quadrant of the XY plane. So you can imagine, where's this region? Your XY plane is here, first quadrant. Okay, so this is the density. Find this. Okay, so what is this? By definition, capital F is a CDF. So you know the definition of a CDF is this. CDF means what is the probability that X reaches up to A and Y reaches up to B? That's what a CDF is. When you did it for, I'm going to black some things out. If I block this out and block this out, does this make sense? If I ask you what is the CDF of X, what would you do? You would integrate from everything from the start to the point of interest, and you integrate the density. That's how you get any CDF. This is now extended to a 2D random variable. You want to know what is the probability that X is less than A and Y is less than B at the same time. So what do? Follow the rules. Draw a picture. The region of interest means I need to integrate the density from minus infinity. Now, I'll tell you why this reduces to zero. I think you also know the reason why. But the complete definition is you need to integrate over everything before A and everything before B for Y. Okay, so digest this fact. Right? The region you want is X before A and Y before B. So you need to integrate over this entire region. Now, can anyone tell me why this goes away and just conveniently just becomes zero? Does anyone know why? Yes. Yeah, that's right. Because the function doesn't even live anywhere outside the first quadrant. That's why. So, but I wrote this for completeness sake because when you define a CDF, you actually integrate from negative infinity to wherever. It's just that in many, many cases, there was nothing there. So this just becomes. So now we're going to put on our calculus hat because I am going to teach you a few tricks. This now becomes a calculus problem. Okay? This is not such an unmanageable thing, and I'll tell you why. It looks pretty bad, but do you realize that they are separable? X and Y can be conveniently moved around. Now, there's a theorem that allows you to do it, Fubini's theorem, but you can go check that out. But basically, when you have integral limits that are not linked to each other, they're just numbers, these functions can move around. It behaves the way you would like it to, basically. So what happens here is this can be split this way. This is correct. It is correct because the limits don't depend on each other. They're just numbers. And the function split very well. If there's an x plus y, then can't do that. But everything is a product, and the limits are independent of each other. See, what do I mean by the limits don't depend on each other? You have just done some examples with me where the limits did depend on the outer variable. Like y goes all the way to 2x or something like that. That's a case where the limits depended on the outer variable. Fubini's theorem doesn't apply. But in this case, it does because the limits do not depend on each other. So I hope you all can see that there's a nice symmetry argument going on here. If I know how to do this, I should, of course, know how to do this. So we'll just focus on this one. Right, because this is just a placeholder. This is a very famous integral, which it would be wise of you to, I don't know, start an integral cheat sheet of your own, because it's going to be something that you can keep in your back pocket like that. It's an ace up your sleeve. It's very, very useful. And I've used it many times in my life. This is the f prime e to the f thing. Well, it's not exactly f prime, but you can massage it to be that way. See, if I ask you to integrate this, there is no closed form answer for this. This is the age-old problem that has befuddled everybody for all time. There is no closed antiderivative for this. But I'm not asking you to do this. I'm asking you to do this. This certainly has a closed form answer. The antiderivative of this is this. Now, why? This is of the famous f prime times e to the f. Why do we like that so much? Because we know that when we differentiate this, we will actually produce this. This is the antiderivative of this. And I recognized it because this is almost, not exactly, because if I differentiated minus x squared over 2, I do get minus x. So you see, I don't have a minus x here. I'm going to put it in. So you can always put a minus here and put a minus outside. Compensate, massage. That's why I know this is the answer. And once you're there, you're home free. Everything else is easy. That's it. Okay, so and that is the answer. This is the joint CDF of the two. So now, did you have a question? Yes. Is there any way? Oh yeah, that's a very good question. You don't have to draw. You look at the nature of these are just numbers. When you have numbers as your limits, not functions of the other variable, then it means that the limits you can move the integrals around. I hope that answers your question. Right? If you find that your limit has a x statement or a variable outside, I'll show you. Like for example, the previous example. See, this is another case where the limits are, but you see, this one you don't have that splitting thing. You know what? This is an irritating function that doesn't help you, right? You can't split it. Okay, and then here's another example where you couldn't. See, this one. This is an integral limit that depends on the outer variable. These are the things that Fubini's theorem doesn't apply. Cannot do anything. You just have to painfully slog through and do it inside first. If they are all numbers, then yes, you can break them into separate integrals like that, right? Okay, so that takes care of that finding the CDF. Find the, basically what am I saying? See, the first question was go find the CDF. Now find the individual marginal densities. This is a joint. From the joint, how do you get a marginal? So this, I need to go to my notes. Okay, we have not covered this yet. So chapter 9, we started this the last time. We can derive the marginal PDFs by integrating out the variable that we don't want. So have a look at my notes again. How do you get the marginal? How does x behave on its own? X behaves on its own by integrating the entire joint density, integrating out the variable that we are not interested in. Is there an analogous argument for discrete random variables? Do you remember? You have a joint distribution for discrete. How did you find the marginal? Didn't you sum over the variable that you're not interested in? That's what you did. That is the discrete analog to this continuous argument here. In continuous world, You integrate out the thing that you don't want. In discrete world, you sum out the thing that you don't want. Remember, I give you a joint table, and then I said, okay, how does X behave on its own? You add it up. You add up all the Y's that you are not interested in. Sum over the variable that you're not interested in. So now you integrate over the variable that you're not interested in. Okay. That takes care of this. So let's do this. So if you look at the what I have here, okay, let's follow the rule. The marginal density of X is, according to the definition, take the joint and integrate out the variable that you don't want, which in this case is Y, because I want to know how X behaves on its own. This is the calculus analog to summing over a joint PMF, and you sum up all the variable that you're not interested in. And you have a table of those. Now, why is it correct that this reduces to, again, 0? Because this density only starts to wake up when X and Y are positive. That's why this, see, this is what we call the complete thing that you need to do. It's just that outside of 0, there is no density 0. So you can start at 0 like that. Are we alarmed at this integral? No, we are not. Everything breaks up as a product. What would you drag outside? Would I drag out all the x's? I would drag the x's out as much as possible. Why? Because I'm integrating respect to y. X now is a constant as far as this integral is concerned. So take this out and take this out. That's fine to do because you are integrating respect to y. Okay. So the next step we should see is this. I have dragged every non-y thing outside the integral, yielding a simple integral of ye minus y squared over 2, which we all know from the previous argument that it integrates to this. And this would be, you replace y equals 0 to infinity. That was the limit of with respect to y. So you actually end up with a density like this. I know there's a lot of symmetry going on and it looks kind of confusing, but everything checks out. The joint density, basically, there's a big finish that I'm trying to gear up to. I'll tell you what it is. You will find that fxx is this. Is it clear to the class that due to symmetry arguments, can someone tell me what is fyy? Is it the same thing? Don't X and Y play exactly the same role, just that they are different placeholders? So what, can you tell me what fyy would be? If fxx is like this, what is fyy? Yes. The same, but X changes to Y. Exactly. And why are we pointing this out? Because this shows that the original density could have been split this way. And what does that tell you? When a density can be split into its X part and its Y part, it means that they're independent. Was there a probabilistic parallel to this that you've learned with me? When the probability of X happening and Y happening can be written as probability of X times the probability of... This is the analog with the discrete product of probabilities. You take products of probabilities when the two events are independent. When two random variables are independent, their densities factor, in other words. And this has to be true everywhere, not somewhere only, everywhere. Just like when you had probabilities, you prove that two variables are independent if every combination you can think of this happening and this happening must always factor. You cannot just try, oh, I found one case. No, it has to be true all the time for all x and y. So these are just the analog. That's why the thing that gets in the way of these things is unfortunately the calculus. But the analogous arguments are easy to understand. Densities of random variables that are independent factors. Right? right? You can split them up like that. Okay, so let's go back to our notes. If x and y are independent, we find that they are joint density factors. And not just their joint density, even their joint CDF factors. And that makes sense. If x and y are independent, knowing that this has happened and this has happened should have no bearing on them happening on their own together. This does its own thing. This does its own thing. Whether they're doing it together or not, they're independent. So, of course, that's not a proof, but that's an easy way to understand it. That knowing that they're happening together does not change the probability of them happening either of them because they have nothing to do with each other. They're independent. All right, like that. Okay, so a few more examples. Let's see. 148. Yeah, see? A company is reviewing tornado damage claims under a farm policy. Okay, let X be the portion of the claim representing damage to the house, and Y is the portion of the same claim representing damage to the rest of the property. The joint density function of X and Y is this. Now, I want to talk about it practically. Do you know why this is a realistic problem? Do you know what we are modeling? What we are modeling is the portion of the claim. Does it make sense to you, therefore, that X plus Y cannot exceed 1? 1 represents 100%. See? In other words, X and Y live in this zone. Why? Because X and Y are fractions. What is the fraction of the claim? What percentage of the claim is for the house? What percentage the Y basically represents the damage to the non-house, the rest of the property. So we know that X plus Y must not exceed 1. So what I want you to do is, can you draw this region? Can you quickly draw this region? The 2D, don't draw this. We are never interested in it. This is a plane. This is some kind of plane hanging around on top of it. I am more interested in your ability to draw the region where the density is positive. So that's not too hard. We know X is positive. We know Y is positive, so that restricts it to the first quadrant already. And we also know X plus Y cannot exceed 1. Right? Try drawing that and see if it makes sense. Right? What should you get? Okay, do you know how to draw the line X plus Y equals 1? Right? Okay, you should have this. I hope you have that, okay? If you have difficulties drawing this, come talk to me, all right? And I'll help you. It's not hard at all. You might not be so familiar, maybe it's in a long time, but to draw X plus Y equals 1, you can draw it as Y equals to minus X plus 1 if you want. And so you know there's a negative gradient equals 1. I don't want to dwell on this in class because I think most of you are okay with this. So this is the region of interest. The total probability over this must be 1. We know X plus Y must not exceed 1. This line is a boundary, because how can you have proportions more than 100%? That makes no sense. So that's the region. So what do we want? We want to determine the probability that the portion of the claim for the house is less than 20%. What are we saying? I want to know the probability that the house claim is less than 20%. That's what I want. I don't care about the rest of the house, or the non-house, the Y part. So how do we do this? So again, follow the rule. Probabilities are integrals over regions of interest. That's the biggest link you must get across. Don't freak out, right? A question like this is harder to see in a two-dimensional world, but just a little bit harder. Where is the region X less than 0.2? Draw the region. It's not too hard to draw. 0.2 would be here. Where is X less than 0.2? We're here. Here, if you are here, then your X is less than 0.2. Don't care about 1. Yes, this controls X and Y ultimately, where they can roam, if you like. But this is the region of interest. So integrate here. Do you agree with my setting up of the limits of integration? Stare it for a bit. Do you agree? Use the coloring argument. Again, there's a wiser choice. It is easier to color in the y direction first. Do you agree? You could do x direction, but then you have to change rules and all that. Because if you color this way, unfortunately, there's a change of rule when you reach this point. So don't do that. Color this way. That leads you to the need to only set up one set. So I'll go through with you. Why do these limits make sense? First of all, if I color this region, and why am I coloring this region? Because this is the region of interest. So I start always at y equals 0. Every line I draw will start at y equals 0, and it would extend all the way to this line. But what's the equation of this line? This line is y equals 1 minus x. So it stops here. And then these vertical lines that I draw will range from 0 to 0.2, and we're done. That's it. That's the probability that you want. Integrate over the region of interest. It is the setting up of these things that can cause them. So when I set exam questions, not for Thursday's exam, but sometimes I just ask students, set this up and then leave it. Don't integrate it. Tell me what you would need to do, but don't do it, basically. I'm more interested in whether you can set this up. Because the rest is just kind of tedious. Okay? Yikes. Sometimes if you ask this kind of thing, right, you have a class of 14 people, you get 14 answers. Because without the aid of actually, now you know why people make these algebraic smart things that can integrate. These things are very painful to do. A lot of bookkeeping and keeping track of minus sign, minus. As I said, I used to like it, I don't anymore. Hate it. Very irritating. So please, for your homework, go use software. Don't waste your time. Right? Unless you want to practice, then maybe do one. But other than that, I really don't recommend doing this. But that's the answer. You might want to practice doing it in the other inefficient direction and see if you get the same thing. And you set it up, then go Wolfram Alpha and see whether you get 0.488. That's good practice for you. Okay, if you want. Let's do another one. Let x and y be continuous random variables whose joint density is this thing. Okay. Now we're getting somewhere. This is, first of all, I can't even imagine what this surface looks like. It's 15y. It's a surface, but we don't care. Can you draw this region? Okay, do that now. Where do x and y live for this definition? I am interested to see if you can draw it. It's not very hard. Try. X and y live together with this relationship. Can you draw the region? What does it look like? And I hope you understand why is the region of interest so important. Because all your integration limits come from there. If you get that wrong, then the whole problem is wrong. That's very, very important. Get the region right. Because any integration for probability, for finding marginal densities, everything starts with that. Okay? Okay, anyone care to describe to me what you should be seeing for the region? The region is on the XY plane. Anyone care to describe what does this look like? A region that's defined by these rules. Y is less than x, but at the same time more than x squared. Yes. Draw a parabola. Anya saying, draw a parabola, draw a straight line, and it lives in any region between the two. So you should see something like this. Very good. So you should see something like this. Notice, I don't care about the 15y thingy. That's it. This is the only way you can follow both rules at the same time. This tiny sliver is the region of interest. So this density is going to integrate to 1 over this. Now, what this looks like, I don't care. Something, 15y, okay? Actually, I think it is z. I can't do 3D very well. Maybe you can, but it's some plain thing, okay? Living on top. Okay, so here's the region of interest. Here's what I want you to do as an ICT with your table mix. How would you find the marginal density of y? How does y behave its own? Take this as a challenge. You need help, just follow. I'll help you. You know that to find how y behaves alone, what do you need to do? You need to integrate out which variable? Just set up that integral. Fyy, which is what you want, Fyy is the integral of the joint dx. And then you know the rule, you want to integrate over all possible x. But where does x actually begin and where does it end? Right? Give it a try, right? Give it a try. This is you know the definition. To find marginals, you integrate the variable of non-interest away over the entire range it can live in, which translates to something specific according to this picture. I want to see how far you can go with that. Right? Try discussing with your friends. What may help? You want to find a marginal density of y? Draw a generic line at a fixed value of y. And then ask yourself, as I move along this line, how does x change? How do I scan over all possible x's? Fix y. When you say fyy, you're saying for a generic y, how does x change as I slice through the region? Draw a generic horizontal line. Don't draw one here, okay? That's kind of dumb because nothing's happening here. Draw one that cuts through here. Right, remember you're integrating x away. Right? Okay, remember, you want to find this? Integrate the joint over x, and I know this is one of those, I would say, pointless definitions. It means integrate over every possible x. But of course, there's a specific thing we should be looking at in this context. This just means over any x that you can imagine. Everything. But of course, only interesting things happen in that tiny sliver of space. How does x behave there? All right? Give it a think. See what you come up with. All right? That's it. Draw a generic line, fix y, like that. Yes. Yes, that's a good action. Let's do it. Go in a positive direction. Because it's plus D, because it's plus D, yes, so you go, so you go positive. By the way, this is yeah, it's just a K1 minus 2. Yeah, and this one is executed. This is executed. This is one position. Yeah, that's all repeated. Does it make sense? Yeah. Draw a generic horizontal line that cuts through this. And you only need to see the point because it has changed rules. Now there will be more complicated examples where different things happen. Yes. Oh, okay. You know why is that? So first of all, it says why is trapped? So I think most of you are getting it. So I'll show you what you should have gotten. All right. Draw a generic line that spears through this thing like that. There is one very subtle thing I want to mention. So you see, again, this is where math sometimes, this used to frustrate me a lot because I would say this, okay, I only had one professor in undergrad that was really good and really cleared things up because I did do this with a professor that was absolutely terrible. And he would give us this definition. These are the things that are correct but not helpful. Now, what does this mean? Well, it means specifically for this case, you only need to look at what happens when your y value is somewhere here. Because nothing exciting happens if you draw a generic line here. Now, I'm going to say something very, very carefully. This is only true for y values that you draw between what and what. This is true for which y? I know y is fixed, but which fixed y? For y's that are between 0 and 1. You know why? If I drew a line here, I fix my y here. Is there anything exciting happening? No, the density is 0. If I fix my y here, is there anything exciting happening? Nothing. So, actually, when you wrote this, what would have been the icing on the cake, which I don't expect because this is new to you, is you write this for y between 0 and 1. Why is that so important? Because densities need to be defined for everything. And can you conclude for y outside that range? What is the marginal density? 0, nothing. And it's not nothing because I didn't do it. It's because if I drew otherwise at other places, there's no density to cut through. There's no probability there. And so the marginal will all be 0 as well. So the complete answer is very good. I was very, very pleased to see that you write x in terms of y. Why? Because you are integrating x. So what's bizarre is you want a marginal density for y. You should get your answer in terms of what? If you find that you're getting an answer in terms of x, something is really wrong. What? You started off asking what y does, and then you got confused in the middle and ended up with the answer in terms of x. No. You state x in terms of y because it is y that you are fixing and x that you are integrating away. What is really hard for students to grasp is this y here is actually fixed geometry. For any y in 0 to 1, this is true. As I said, draw a generic representative line. Like, people like to use your token, whatever, your token line. Draw a generic line that represents all lines between 0 to 1. And there you can do. If you took the time to test if is this a legit bona fide density, will it integrate to 1 between 0 and 1? You will find it does. You have generated a density. It is a true blue real density. It does integrate to 1. It's how y behaves below. Right? So I don't think I asked this question, but can you reverse it? If I asked you, find the marginal density of x. This is not a question on the example. What would you need to do? To find how x behaves on its own, you would draw a generic line like this. In some x position, and reverse the whole argument. You would have to ask yourself, okay, if the only exciting lines to draw are x's inside here, once again. Nothing exciting happens outside, nothing happens here either. So all those are 0. So for any x here, then your x would now be written, you would now state your x would come in at different values. So you would integrate y away like that. And then you get your argument in terms of x. So you could reverse the process. The integral will be slightly different because if you integrate with respect to y, then clearly because of the density, the nature of density, there's no symmetricity here, so you actually get a different density for x. X and y do not have a symmetric relationship here, obviously, because the density is 15y, not 15yx or something. There's no symmetricity between x and y here. Yes, it would also be a 0 to 1 argument, but it's a different thing. All right, so that's actually how you do things like that. Okay, so I think we've talked about it. We'll revise this a bit more as we go along. Let's now talk about expected values. More calculus, but again, we are not bothered with that because we usually use software to help us. But it's more important for you to set up the integral. So let's go back to our notes. How do you find the expected value of functions of continuous random variables? And I give you some examples, okay? I have 2 random variables. Here's a function of them together. And please bear in mind, right? This is also considered a function of 2 random variables. It's just that y is not there. It's x plus 0, y. You know that warning they give you in aeroplanes? Know where the exits are, bearing in mind that the nearest exit could be behind you. Have you noticed they always say that? It's a legal requirement, I think. So bearing in mind that a function that looks like a function of 1 variable is actually it's also a function of 2 variables, just that the other one doesn't feel. All right, so I hope this is not coming as any surprise to anyone. Expected values are found how? Take the function of interest, dump the density next to it, integrate the variable. It's just that the calculus part is getting worse and worse. But the idea is the same. Take the density, join, because x and y behave jointly together, put the function of interest that you want to find the expected value of, and integrate. Now, again, this is an unhelpful kind of thing because it means integrate over anything possible in the universe. You have to set it up according to the precise thing that you want. So, if you know this, and then all properties of expected values, variances, covariances, everything, it's analogous and exactly the same. All the rules about can constants come out, do you square? All those rules are the same. It's just that how you find these expected values are by integration, not by summing. That's it. All the expected value of AX, AEX, and things like that. All these things apply. It's just that how you find the expected value is by calculus. Okay, so let's look at some examples. So here, X represents the age of an insured car involved in an accident. Let Y represent the length of time the owner has actually insured the vehicle at the time of the accident. Oh, okay. Now, again, fortunately, is this a simple region to draw? X is between 2 and 10, and Y is between 0 and 1. Very easy, rectangular. Okay. So draw that. Don't worry about this. As I said, don't worry about this. This function is some like a rug or something, right? Floating on top. We don't care. Draw this function, right? On the XY plane. Calculate the expected age of an automobile that's involved in an accident. So you see, you want the expected age. Now, which variable is the age? X, right? Which means I actually want EX, expected age. Do you agree with the limits that I put on? This one, there's no advantage doing X or Y first. Doesn't matter. So X from 2 to 10, Y from 0 to 1. That colors the whole region. No slanting lines and curves and all that, nothing. One very important point which I want to say now, and look, I want EX, right? So I dump X here. I want the expected value of this function, so dump it in. Then the density is this equals. The important thing to note is, and I would tell you, be very careful. When you are finding expected values, you don't integrate over a specific region. You integrate over everything. Notice there's no smaller box or something like that. Those are probability. That's different. If you're finding a probability of something, X and Y, where they hang out, then you have a sub-region and you set up the region. Right? Expected values integrate over the entire region where the density is positive. So I have summarized this in a note that I made here. And I'll show you that there's still one page I want to talk about. So you see, probabilities are like that. You see, the entire region is this one. That's where the density is positive. But I am interested in the probability that X and Y live here. This is not an expected value, probability. Then you integrate over the smaller region of interest. But if I have a 2D thing going, see, same thing goes here. See, this is a probability question. I want to know what is the probability that X and Y hang around here. So you integrate over this specific place. But if you want to find expected values, then you integrate over everything, the entire support. Don't set up sub-regions and all that. You integrate over the entire place where X and Y live. Because expected values are, according to the definition, every possible X and every possible Y. And that is why you don't have a sub-region. So sometimes when you learn a little bit of these things, you can suddenly get a bit mixed up. Like, hey, why set up? There's no region to set up or sub-region because this is not a probability. This is expected value. So please be careful. This is, of course, analogous to what you have actually seen when you did 1D integrals. For example, when you had the simple case where you have a continuous random variable, this is y is your random variable, the density is given by fx. See, if you want to find a probability, you integrate over the region of interest. For example, x lies between a to b, you integrate from a to b. And I've drawn it this way to be consistent. The a to b is this piece. You're integrating over this little piece here, which translates to this. All right? And this has, of course, a 2D parallel when you have a box or a plane like that. So the point I'm trying to make is please differentiate between probabilities and expected values. Expected values are always found by integrating over everything. Probabilities are found by integrating over the region that you are interested in. All right? Okay. So let's go back to this. And then the rest is there's nothing very much to talk about. It's just very tedious and all that. This is the final answer. Yuck, right? Okay. Nothing special here. So I only want to talk actually about the setting up of the limits and being careful. Now I want to ask a question to the class. Is there another way to get EX? Anyone have any suggestions? Anyone have any ideas? Not here to do it, but do you have any idea how you could get EX some other way? Do you know what I'm asking you? This is a way to get EX, but is there another way to get EX? Yes. If you go and derive if you get fxx, then why just goes riding into the sunset? It goes away. It just becomes a one-dimensional problem. You can do that as well if you want. See? Now, again, this is, again, I don't have time to do all these things in class. Or maybe I will make the time. And maybe we will do that. Try to find EX the other way. So in other words, and you can do this as an ICT, right? Maybe. So here's what we'll do. Here's the joint. Can you derive the marginal for X alone? And trust me, this is a much easier one. There's no slanting lines or curves or whatever. Get the marginal density for X, then go find EX the usual way, as if Y didn't even exist. See if you get 579 like that. See if you can do that, okay? So derive how does X behave on its own? This is the joint behavior. How does X behave on its own? So draw a generic X line at some fixed value of X and integrate Y away and see whether you can get the answer, right? Right? Start by getting fxx first. How does X behave on its own? It's not that bad. That's not too evil of an integral. I think it's within your reach. It's a little bit tedious, not too bad. Oh, I was supposed to bring the pins to the cards. I know, I forgot. So I'll bring it on Thursday. Okay? All right.
Is there a specific day that you
We try to do it together as a department on what we call Spirit Week. Not as spooky as it sounds. But yeah, so this is officially. In fact, there's some more related show or something on. I don't really go. Count it out. That's right. So we can, yeah. So that, yeah, we try to coordinate these things. I just came directly to my car and I just pack it up.
So are we doing it integrated or just a- Okay, no.
So do you agree that your marginal density for x should only be non-zero between 2 and that's the only place where the action happens. Nothing else happens outside there. That's right. It's not going to be very tricky. I think the density is going to be kind of ugly. And then try to integrate over the entire region where x is and see if you do get 5, 7 out of 9. I'm so sorry. I'm hearing all these terrible numbers coming out. Yeah.
Okay, and then for 2. Okay. Let's hope we get a negative for it. Maybe we have to post it into grade. Okay, let's 5 minus 4. Oh.
You know, I don't even mind if you tell me the integral that you want to do. You can go use root alpha. If you don't want to deal with this, you can. Just say so. That's all. Right?
So that's now.
Okay, that's also.
Okay. You have the density. So the difference is I did anyway.
Okay, so let's see. Let's have a thought.
Right? You want to get you should get one. That's right. And that is one way.
Wait a minute.
What?
This integrated, right? Shouldn't this be divided by 2 and not by 3? No, because
We
we
could,
could just.
right, it's a constant.
Yeah.
You'd be doing
It's very important to do.
like 0, just that is every.
But just say something. So annual marginal correct. It is not so much.
What is going
It's
on?
growth.
Good
job. That's exactly right. Very good. Yes.
Okay, we're quite unsure where things
Okay.
are going on.
No, let's see. You can do yes, because you have this. You can do it while away and while always goes on. Yeah, this is the best but and this is true, and I would encourage you to have this culture of saying this is true for yes,
Okay.
any x equal to because the density must always check that on. You have to tell people where this is true.
Okay.
So to do that, no integrate from to do that. No, you did this and you did it. You're integrating.
Oh, because
You're trying to find EX. You're not
so
you're-
yes, because so then we dump in the function.
just add an X. Just add an X.
Oh.
See?
So,
Right? So you're not all gone. So you just have to
perhaps you're okay. X are positive sets of values.
Yeah.
Or our function or interesting.
Exactly. Exactly. That's right.
Okay, so now for this,
Oh, okay. And we will do one final ICT. Not asking you to do any more calculus. Set up the limits that will give you this probability. This is a new question, all right? This is not a bad region. This is an easy region. But how do you say what is this probability? So draw this region, which is a subset of this region. Just set up the integral, don't do it. Set up the limits.